Hi, so this is number 7 actually in our Talking Heads series for the Land Use for Net Zero People and Nature Hub. This comes from the Soils Tag, and the Soils Tag is the topic advisory group on soil health and carbon dynamics. And today we're going to interview Joel Williams. So I'm going to pass over to Pete to introduce him.
Thank you, Ellie. So welcome, Joel. Joel Williams from Integrated Soils is an independent plant and soil health educator and a consultant who's worked extensively in Australia, Europe, Canada, where he's currently based. He has a keen interest in soil health, plant nutrition, and plant and soil microbiomes, and how these may support the development of sustainable production systems. Joel has a Bachelor of Agricultural Science, specialising in plant and soil dynamics, and an MSc in Food Policy, where he explored the motivations and barriers to the adoption of intercropping. Joel has a passion for teaching and sharing a combination of scientific and practical information, and has lectured to farming audiences internationally. So we're very lucky to have you. Thanks, Joel.
Pleasure.
So I'm going to kick off the questions. So my first question is, what conditions need to exist in order to maximise carbon sequestration within rotations, cash crop and cover crop?
Sure. As I'm sure you know well, there's many variables here. There's many aspects to consider, but I think we could bring it back to one of the really important things, which it all starts with photosynthesis and plant growth and biomass production. So anything that's going to govern how much carbon we can get out of the air and bring it into plant biomass is going to be a really first and important step that's going to drive that. And then really from there, it gets a lot more, I think, maybe nuanced, the discussion, and more details we could kind of dive into. But key to this discussion is ultimately more roots. We need a lot more below ground carbon, more root mass, root biomass, and some of those root exudates that come with that. It's really the below ground carbon that is the main driver of building soil carbon. So, that would be discussions around potentially more perennials versus annuals, would be part of that discussion. There's been some interesting work looking at root to shoot ratios of modern plant varieties compared to some of the older heritage types. And we see that definitely the reason we've increased yield with modern breeding is because we've encouraged those modern varieties to partition more of that photosynthetic carbon above ground. And that's been a trade-off to below ground. So we see a lot smaller root mass in modern varieties, and that's been a contributing factor to maybe some of our soil carbon declines as well. And then there's the discussion around nitrogen inputs. Nitrogen inputs are a bit of a double-edged sword. A little bit can be positive for encouraging biomass, but actually excessive nitrogen inputs can start to have very suppressive effects on particularly on root biomass production. So again, mismanagement of nitrogen is something else that we really need to focus on closely. But really all of those things kind of come together to also think about the role of managing plant nutrition. I think to your question about cash crops, I think we need to better manage plant nutrition, and that nitrogen would be a good example of that for better cash crop production in terms of particularly, again, root traits. So is there more root stimulation, better nutrients for root stimulation, maybe biostimulants for better root stimulation? And then I think for our cover crops, it's really then about trying to choose plant species and or varieties and cover crop blends that have that higher root to shoot ratio. So choosing some of those deeper rooted and more heavier rooted plant species for those cover crop mixes. So I think that would be some of the key things. It's really about maximizing those inputs into the system. But of course, then we've got to also minimize the outputs. And that's where you'd think about things like minimizing soil disturbance and cultivation. So we want to encourage much carbon in, but we also want to try and minimize some of those losses. Yeah, I think that would be the main things that I'd think about.
Yeah, great, perfect.
Yeah, really interesting. So I was going to ask how important above ground biomass incorporation is, sort of as opposed to root exudates, and why. You might feel you've already covered that.
Yeah, I alluded to it there, that it's really roots play the leading role. It's roots and not so much the shoots, the above ground biomass. Don't get me wrong, the above ground biomass does make a contribution to building soil carbon, but it is a minor. It's not the leading role. There was a great review study back in 2017 that suggested that they summarized a whole bunch of other studies and summarized that roots are around about 5 times more likely to kind of form soil organic matter than an equivalent mass of above ground biomass. So again, it's not to say that above ground makes zero contribution, but it's just that roots really play that leading role. And part of the big reason for that is primarily just their location, just where we find roots that are already down in the soil, where then the biology, particularly that microbiology, can access those roots and digest those and transform those ultimately into soil carbon. Whereas the above ground material, it typically sits on the soil surface, maybe as a mulch, as a litter, as stubbles, more on a surface layers, which is then why because it's sitting up on the surface and not down in the soil, that means it's more prone to then some of the oxidation, the sunlight, some of the carbon losses of part of that cycling. So generally it makes a lesser contribution to soil carbon because of that. Now that said, I think there's caveat there. I think where we have soils that have much better earthworm contents, of course those earthworms, they're going to come up to the surface and bring some of those surface residues down, the above ground matter, they're going to pull it down. And when they do that, I think you find that the above ground biomass can make a bit more of a contribution where we do have good earthworm activity. So I think that would be a particular caveat there. And then beyond that, yeah, you're alluding to this other really interesting part of the question is, well, what about the root exudates? Typically in agriculture, we've been very focused on the plant biomass, the litter, the lignin, the cellulose, the roots or shoots. But we've a little bit traditionally have a little bit not thought so much about the role of these liquid carbon, the root exudates, sugars, amino acids, other lipids and things that the plants excrete out of the living root systems. And these are smaller, lower molecular weight compounds, and these are highly, highly digestible to microorganisms. And it is that high digestibility of these carbon sources to those microorganisms that makes them very interesting, because the biology can so much more efficiently, much more easy and efficiently eat that carbon, digest and integrate that carbon into their bodies and grow their microbial biomass. And as they do that, they form a really important part of the soil carbon, because as microorganisms, first they grow, they produce biomass, and then when they die, these decaying microbial fragments and bodies, this is called microbial necromass. And it turns out that it's this necromass, the dead bodies of the microorganisms, that is particularly useful and particularly good at forming the more stable fractions of carbon in the soil. So they have a particular affinity to stick to the soil mineral surfaces and form a very stable fraction of soil carbon. So in that regard, there's some really recent and interesting work looking at then the role of these exudates. And look, there are many variables here. It's a very complex world down there in that rhizosphere, and we are only beginning to unpack it a little bit. But one of the indicators that suggests is important is this point about carbon use efficiency. And it's the fact that those root exudates are highly digestible means that they are more efficiently converted, fed on by the biology, and therefore converted into that biomass and necromass. And that high carbon use efficiency makes them very interesting. And I think that for soil carbon sequestration. And that's why when we look at things like the soil health principles and regenerative ag principles, very commonly we talk about that living roots soil health principle. And that's the practical implication of this, is that the more we can keep the soil covered with green plants and living roots, it's only living roots that provide us those living carbon sources, those root exudates. And so that's where that soil health principle becomes really, really important to drive this particular pathway of soil carbon formation.
Yeah, that's great. You talked a bit about the we need to switch out plants with a root and more root mass, because we've traditionally bred that out of, to sacrifice the root mass for the bit that we harvest, what's going to actually be the yield. In terms of in addition to swapping out the plants and using better rotations, what can the farmer do? What agricultural management practices enhance soil carbon sequestration?
There was a really good review paper from Europe back in 2021 that was looking at optimizing carbon sequestration in croplands. And in that paper, specifically in croplands to start with, they found very clearly that the number one best thing that helps to build soil carbon is the use of compost applications, manures and compost, etc. Now, of course, the problem with that, it really stood out neck and shoulders above some of the others, and I'll mention a few of the others. But of course, so that's good because composting, when we compost, material, manures, etc., we are going through a microbial digestion process already. So it's the biology that does that composting process, and as they grow and die, they're forming a lot of these microbial wastes and this microbial necromass that then becomes stabilized in the compost. So that then when we apply that compost, it's a much more stable form of carbon that's more likely to persist and remain in the soil for a bit longer than some of the other plant litter forms. So it's really good and it's a clear winner. But the problem with compost is that, compost applications to soil is not necessarily relevant on all scales for all soils. We're taking plant material from somewhere else, we're transporting it in, we're composting it. And yet that's a great soil conditioner and great soil amendment, but the plant carbon, the original source of that plant carbon, where it came from, has come from somewhere else, from off land. So it's where the economics of compost stack up, where farmers can access it affordably and not pay for too much freight, these types of things. Look, it's a fantastic way to build carbon. But in terms of the practices of building soil carbon in situ, right there in the soil where we're growing, that's where then things like reducing tillage was very important, the use of cover crops, and again, deep-rooted crops. Those were kind of the next in line that had the biggest impact in terms of building soil carbon. So yeah, again, like more roots, more plants, more diversity, more cover crops, keeping that soil covered, more living roots, and then just trying to minimize those disturbances to the soil. So that was kind of the main things that they found. And I think beyond that, then in general, we would also say that, look, grasslands, perennial-based systems and grasslands, very clearly they always have a lot more soil carbon than our annual-based systems. So however we can kind of integrate potentially livestock and integrate a perennial phase, and I'm very excited. I think in the UK there's a lot more discussions just in the last few years, especially about using a perennial fertility herbal ley or perennial phase in the arable rotation. And I think that is an excellent strategy because that brings the benefits of the perennials and the roots and that animal interaction, and that helps to build soil carbon in those cropping systems, so that when we go back into the arable annual part of the rotation, sure, we're going to maybe use that fertility, but that's okay. If we're building fertility, then we can kind of redraw on the bank account and use that fertility for cropping, and then come back to a fertility building phase in the perennial phase. So I think generally then, however farmers can bring a bit more perennialization into their systems is always going to be advantageous.
Great, thanks, Phil.
Yeah, that's really interesting. I mean, the flip side of that is, what practices do you think reduce or eliminate carbon sequestration? And I'd be interested to know as well if, when you're referring to what happens, does your work look at sort of what happens better in different circumstances, for example, in different soil types or at different depths?
Yeah, sure. So, well, that same paper that I mentioned just earlier, it also outlined public enemy number one to soil carbon sequestration, and it was bare fallows. That bare fallows actually led to a decline in soil carbon. It wasn't that they had the smallest gain, it's that they actually had a suppressive effect on soil carbon, and bare fallows are arguably the number one enemy for soil carbon sequestration. So again, that's why by default, when we talk about perennial systems, they have that automatic advantage of being perennial and permanently covering the soil, which is why a big part of why they have those benefits. So yeah, avoiding fallows, I think, is number one. And then beyond that, okay, we could kind of look at that question in reverse. Yes, sure, maybe avoiding excess tillage, trying to minimize that tillage as much as possible. And again, I mentioned earlier in your earlier question about the role of nitrogen. Excessive nitrogen can also start to kind of mine carbon out of the soil. So wherever we can try to use much more modest amounts of nitrogen is also going to help. And again, that's a bit of a fine balance, but it's the excessive applications that typically can be a lot more damaging. So So yeah, I would avoiding tillage as much as possible, trying to avoid over applications of things like nitrogen would also be important to keep soil carbon levels where they are.
Yeah. So,
No, oh, and then you mentioned some other points there about yes, yeah. So you're right. Like things like soil type is also really important. So yeah, there is always, this in this whole discussion of soil carbon sequestration, there is so much context and nuance that needs to come into the conversation. The kind of the blanket statements on what's possible or the potential of this kind of thing, it really has to be a much more localized, specific, nuanced kind of conversation because yeah, different soil types very much, and different climatic conditions, different moisture contents that all govern how much biomass we can produce or how well those soils can then hold on to that carbon that gets integrated. These local specific factors definitely have a big impact. So yeah, for sure that needs to kind of we need to dive into those details as well on a case by case scenario.
is there a certain minimum amount of soil carbon that you have in the soil in order for it to improve? I'm saying, is there a sort of baseline organic matter level that you have to be at to have a healthy soil so that it can gain more? And the other side of that question is soil carbon doesn't continue forever, right? You just can't keep putting it in and the soil carbon goes up. So what are your views on that sort of
Mm,
equilibrium or saturation issue?
Pete, sorry,
yeah,
can we cut there? Can you start the question again? Because you cut out at the very beginning.
Okay, if I can remember what I said.
It was a good question.
So,
it was
so,
good.
so Joel, is there a certain level of organic matter that you need in the soil? Does the soil need a certain level enough to be healthy to gain more soil carbon? That's the one part of the question. And the second one is that soils don't just continually increase in soil carbon forever and ever, do they? They reach some sort of new plateau. So what are your views on that sort of new equilibrium position, or some
Mm,
call it saturation? Can you just
mm.
give us your views on those two things?
Sure, sure. Yeah, so that's a funny one, isn't it? If you look at things like how well does soil organic carbon, correlate, say, with, for example, things like yield, you would say that generally across the board, it doesn't necessarily always correlate so well, but in some instances it does. And particularly then, say, for example, the lighter, sandier soils on your very lower soil organic matter soils and particularly sandier soils, any increase in soil organic matter that you can gain there will actually then start to have bigger, distinct impacts on productivity and profitability. And so in those lower ranges, yes, it's very important to build as much as you possibly can. But once you start to hit, say, above 2%, you start to lose that kind of very clear benefit in terms of yield anyway. And of course, that benefit of yield is really driven because we're increasing biomass production. However, it's an interesting question. Yeah, I agree that it makes more sense. We all appreciate the value of soil organic matter. The more soil organic matter generally we can have in our soils, we're going to see better soil chemical, soil physical structure, chemical biological functioning. So we're going to achieve better soil health and better soil function. And with that better soil function, sure, when we then grow crops and plants in there, they're going to also produce more. And so yes, I think it makes sense that there's a bit of a threshold there where if we can get carbon up, that actually improves soil function, that improves productivity, and that then has the potential to further increase soil carbon sequestration. So yes, I do think therefore it is really important through that line of thinking. And that leads us then to your other question there about the saturation and the carbon plateau. So yeah, this is a bit of a hotly debated question at the moment in the world of soil science, and I alluded part to answer this question. We have to unpack this a little bit, but so there are different fractions of carbon in the soil, and maybe we can go a bit deeper into this in one of our latter questions, but. The fraction that I mentioned before, the microbial necromass, the dead bodies that sticks to the soil particles, that's often called mineral associated organic carbon, and that's the fraction of soil carbon that chemically is stabilized chemically by sticking to the negatively charged surfaces on the sand, silts, and clays. And so it is that fraction then that is dependent on the mineral surfaces to form. So the analogy is a car park, a light sandy soil, as all farmers know, a light sandy soil holds less water, holds less nutrients, and it also holds less carbon for the exact same reason. It's a smaller car park compared to a bigger heavy clay soil that has a whole lot more chemical surfaces, colloids, which can bind to and stick that necromass that can stick to it, and therefore we have much greater potential to form soil carbon in those clay soils. And the point is that once those car parks are full, whether we're talking a lighter soil or a heavy soil, once we fill all of those negatively charged surfaces, once we fill that car park, that form of carbon, that mineral associated, that is the fraction that, yes, does saturate. For that very obvious reason, it is dependent on the mineral surface to form. And once they're full, they're full. So that is the fraction. Now, but we do have other fractions of carbon in the soil, like the particulate organic carbon, and that's the other fraction that is, we could call that the fraction that is still the plant carbon that is going through a state of decay. It's a continuum of decay of lignin and cellulose and plant litter that's getting broken down, decomposed into smaller particle sizes. So it's this big old continuum of some complex plant carbon all the way down through to some of the smaller fractions. And all of that kind of carbon that has not yet been eaten by a microorganism, it has not yet been digested and turned into the microbial biomass, this we could kind of summarize as calling some of this particulate organic carbon. And that carbon is not dependent on the mineral surfaces to be there. It normally is stabilized and sequestered through aggregates, through physical entrapment, through aggregation, etc. And that is the fraction that does not saturate. So the example of this would be a peat soil. Peat soils just keep growing and dying. That plant material just keeps on building. So those soils do not saturate, for example. So it's this particulate fraction that does not seem to saturate. However, the problem with that is that the particulate organic carbon is a lot more vulnerable in soils. It's a lot less stable, so it cycles in and out a lot more. So it's much harder, although in theory it can sequester infinitely, in practice, it's a lot more vulnerable to being cycled in and out of that system. So we generally don't see it accumulate to really high levels unless in a very context-specific way, like a peat bog, where we, water anaerobic and saturate that system, and therefore then that carbon gets stabilized. So then that's I think a really interesting part of that little debate and discussion. And I think that the next piece there is that, okay, well, what about at depth? What about soil depth? And that's where I think we do have an opportunity to sequester a lot more of this mineral associated carbon. The more stable fraction is that if we can get more roots down at depth and get some of that root material down, but also some of that liquid carbon, the root exudates, and deposit those down at depth, depositing carbon at depth is also going to make it more stable, because generally it's also the carbon at the surface of the soil that's, again, more cycling. But the more deeper we can get that carbon, and again, key to this is perennials and deeper rooted plants, and then getting some of that particularly liquid carbon deposited at depth, you're also able to then sequester still a lot more carbon. And a lot of soil types, not all, but I would say most soil types actually become more clayey at depth. There are some soils that are sand-based, sandstone derived, and they often become sandier and lighter at depth. But most soils become heavier and clayier at depth. And so that's the real potential, is that with better management above ground of plants and those rooting depths, we can deposit much more of this plant carbon at depth. And I think we have a long way to go to still increase soil carbon. So look, although there is a saturation limit, a plateau, and that's an important discussion to have, I think that in agriculture across the board, for most soil types, we are a long way away from that point of saturation. So yes, it's important, but practically for right now, we just need to get on with it and manage the system better with deeper roots, etc. Because we got a lot of gains to make before we need to kind of even start worrying about that, I think. But yes, it's an important point in the broader discussions of, how big of a tool can soils be for climate change mitigation. So yes, we need to have that conversation. But I think practically most soils have depleted carbon, and we just need to get on with kind of building a
Yeah.
lot more of it. Yeah,
So to use your car park analogy, what you're saying is we've got a multi-story car park, and some of those deeper layers of not the car park isn't full. So if we can
absolutely.
get the carbon down there in the multi-story car park, there's some maybe unsaturated sites that we can increase the soil carbon in those layers. Yeah, good
That's
point.
right.
Yeah,
Spot
well
on.
explained.
Spot on.
Ellie.
Yeah, so really interesting. I was thinking in terms of the kind of subterranean levels of the car park. Um, there was a recent study, a European study, that suggested something like a third of EU soils are compacted at depth. That subsoil compaction is a real issue, and you've talked quite a lot about farming systems, and we've talked about the potential of reducing tillage. How do you marry those two things of this kind of potentially compacted layer that we want to get things into that might not quite at the moment be receptive because it's had a few decades of very heavy machinery going over it,
Mm.
especially in
Mm.
the UK where we have it's just potentially more vulnerable soils than on those lovely flat prairies.
Yeah, that's right. I really agree. From my experience of now traveling to many different countries and many different parts of different countries, I have to say that I think compaction is quite possibly the number one most common thing that I just keep seeing everywhere. Like it doesn't matter the context that, and even in both in cropping, but also even in perennial systems, grasslands, etc. I agree that compaction is a really, really common and major problem. And yeah, you're right. It would be a limitation to some of these benefits that we're talking, or strategies and things that we're trying to use to build carbon. So yeah, it's all good to talk about deep roots, but if deep roots can't get down there, then they're not going to be fully functional. Now, look, deep roots can also help to address compaction and cure that problem. But I think then there's a lot of kind of interest, in the regenerative movement around the role of some of these diverse plant mixtures, some of those deeper rooted species in those mixtures, and their potential to kind of get down and alleviate compaction. And indeed, they can do that for sure, but they take a bit more time. And look, I'm not opposed to some mechanical intervention to in the short term. You're treating a symptom to let's say a deep rip or crack open that compacted soil, for example. Look, I'm not opposed to one-off strategic interventions like that, as long as we acknowledge that that is not addressing the root cause of the problem. The root cause of the problem is a lack of roots, a lack of deep roots that keep that soil open and not compact. But it is treating a symptom to crack that soil open, so that when we marry that up with some of those deeper rooted cover crops or deep rooted pasture species blends, etc., that then those plants have the opportunity, a short-term opportunity, to get down there into that cracked soil and get those roots down at depth, so that they prevent that soil from just re-slumping back together. So I think that strategic mechanical interventions I'm not opposed to. I think we should embrace the minimize disturbance mantra, but minimizing doesn't necessarily have to mean never ever. So as long as that symptom treating is coupled with a kind of a strategy to address the root cause and get deeper roots down there, I think it can be okay. But I agree that compaction is a really common and big problem. Yeah.
So kind of marrying up that, I guess it's the science and the theory with those nuances around husbandry, where you are and what's happened previously, in order
Mm,
to get a good trajectory going forward.
mm,
Um,
yeah.
so you talked about going back to the sequestration question. Do you see that carbon sequestration rates in soil vary internationally? And do you have any ideas about what the implications are, if so, for UK farming?
Mm. Yeah, that overlaps a bit with your other question too, about all those different specific local contexts and nuance, and that's right. I mean, around the world, look, there's many different, as you know, even a small country like the UK has so many different soil types, and the true also is true of a lot of the other bigger countries as well. And similarly, so much different climatic conditions and different soil types across that. Um, and so, yes, all of these things are important because, as we just mentioned, clay soils can hold more carbon than sandy soils. So that's a big part of the soil type discussion. But then you've got the climate and the rainfall and the moisture that, so, well, how much biomass can I grow then? Whether or not you've got a sandy or light soil, is it in a more high rainfall zone or a lower rainfall zone? And you need water to grow carbon. You know, you need water to grow plants, and that's how you're going to get your CO2 into the plants with water. So water drives this very much so as well. So it's not therefore just about soil type, it's then about what is water availability in that particular local climate, in that local area, coupled with then the specifics on that soil type. So yeah, so you map out those various different combinations, and you've got all sorts of different kind of potential carbon sequestration, different rates and potentials around the world. And I think that despite all of that, I would echo my previous comment too, that pretty much I think you can look at all agricultural soils and none of them are really close to that plateau, that saturation phase. So despite all of those differences, I think there is still good potential to build soil carbon in all of these different contexts. But yes, the ceiling of that is going to be different in different places. But still, I think everyone is below where they could be. So that's why we need to be having these important conversations more generally. So, yeah, I've just come back from Australia. I was just there for a month, touring around, and for example, in their context, of course, building soil carbon is much more difficult because of the low rainfall. They do have some big heavy clay soils, but some of those are found in very dry regions. So therefore, the water is the limiting factor that therefore limits production and limits the potential amount of carbon coming into the system. So sure, carbon sequestration potential in some of those drier contexts is going to be a lot less than, say, in the UK. Plus, you've got warmer temperatures. So with warmer temperatures, carbon is going to cycle a lot more in and out a lot quicker. So it's harder to sequester carbon because there's more microbial activity, which drives some of that carbon back out into that cycle. So I think in the context of then UK, in that context, you have a lot of advantages. You have a more temperate climate, and certainly more temperate climates have better ability to build soil carbon because of those cooler temperatures. And then secondly, I think we do have a lot of variable soil types in the UK, including many clay soils. You've got many clay soils around. You've got a whole range of different soils, of course, but also your chalk soils and things as well, which can also hold on to some of the soil inorganic carbon. But generally, you've got a lot of other clay soils. So I think when you couple together more clay soils and a more temperate climate and a higher rainfall area, you do have the perfect conditions for good soil carbon. So I would say UK has very, very good potential for soil carbon sequestration. But I would also agree with you that I think compaction is a really big problem in the UK, and it's that high rainfall benefit that you have that's also a curse, because that high rainfall can actually compact the soil over time. If that high rainfall is not infiltrating and it starts to sit and puddle on the surface, that's a lot of weight of soil, weight of water, tons and tons of water pressing down on the soil if it's not infiltrating. So as soon as we start to see puddling and ponding on the soil surface, this is also not good. And we do see a lot of this in the UK. So I think that you're right. Although you've got very good conditions and potential for carbon sequestration, there are always limiting factors. And I think the compaction would be one that would need to be also addressed and focused on in the UK context.
Yeah. So what are the key forms of carbon that we get in the carbon cycle, and particularly in soils, Joel?
Sure. In terms of that carbon cycle, we've mentioned that a few times now, that word, haven't we, through the course of the discussion already? And that word cycle is obviously just pointing out that carbon is moving in and out in different forms. And so, of course, again, it all starts with CO2, that's your atmospheric carbon. And then through photosynthesis, we bring that into the plant. So then we have a whole range of different plant carbons, and that could be sugars and lignans and, all sorts of things that basically are made up of the plants. Now, some of that carbon comes down into the soil. So then you've got the biology in the soil. So we have things like the microbial carbon. As they feed on that plant carbon, they turn it into microbial carbon, or some of that necromass carbon that we also mentioned earlier. So you've got that as another pool. But once it's the microbes that play that really important role at transforming plant carbon into soil carbon. So as they do that digestion and breakdown and transformation, ultimately then the biology turns the plant and their carbon into soil carbon. And there's different fractions of that soil carbon. We alluded to that in that last question. So there'd be a few others there. Things like dissolved organic carbon would be another one that we find. That's some of the carbon that's highly available dissolved in the soil water. There's that particulate organic carbon, that's all of the plant in the continuum of decay that I mentioned. The mineral associated carbon, that's the necromass stuck to the mineral surfaces. And we've got a few other things like charcoal carbon or pyrogenic carbon. That would be some of the discussions around biochar or from charcoal from after post-fire recovery. You can often have bits of these pyrogenic carbon in the soil. And then the last fraction there would be things like the soil inorganic carbon, things like carbonates. That's where some of the chalk soils of the UK have quite a lot of this fraction of carbon in calcium carbonate form. So those would be the main kind of fractions in a plant soil context as part of that carbon cycle.
Great, thanks, Joel. And now going back to this question of carbon cycling or carbon sequestration, Henry Jansen wrote the Canadian soil scientist, wrote a great paper a few years ago talking about the tension between wanting to keep your carbon cycling, because that's good for fertility of the soil and growing your plants, or sequestering the carbon, just keeping the carbon where it is in the soil. So there's a bit of a tension between the two. Is it a tension? And what do you think about that?
Yeah, I think we need both of them. But I think he's right in what he was trying to raise awareness of through that paper, which is spot on, which is, well, actually, the first step is carbon cycling. If you're not cycling carbon, you're not going to be able to sequester it anyway. So I think he was really spot on with that awareness around that. And yeah, I agree that you have to get cycling as a first step. And we want carbon to cycle. Yes, we want it to come in, and yes, we want it to sequester it to build soil carbon. But if carbon's not being released, then it's also not contributing to the function of the whole system. And the perfect example of that is when we think about microbial respiration and CO2 release from the soil. We often, from a soil carbon sequestration point of view, we would look at that as being a bad thing and as a wasteful thing. Oh, we're losing CO2 back into the atmosphere. However, that's an important contribution of CO2 for the plants. And, it's no wonder that plants have the stomata on the underside of their leaves. So it's the underside of the leaves that are breathing in this carbon dioxide that is coming up from the soil, up from microbial activity and microbial respiration. So I actually think that we do want good cycling. We do want to encourage some carbon coming out, because that's going to provide CO2 that the plants can also use. And again, like that point about that CO2 cycling and respiration, I think also really speaks to the importance of that soil health principle of green cover or living roots. We often talk about soil armor, so keeping the soil covered, and that could be with mulch or residues or litter, or it could be with green plants or living roots, green cover. And the big difference there is that when we have that carbon cycling and microbial respiration in a bare soil or in a soil that just has brown cover, stubble cover, then that CO2 that's being released is being released back into the atmosphere because we have no green plants, no currently functioning living plants. So by embracing that living roots principle, that means that when we have green cover over the soil, and therefore when we have some of this carbon release, this cycling, well, then we have green plants there ready to capture that and make use of that. So then we are contributing more to that cycle and losing less through just the actual CO2 losses. So I think that the modern day spin on that soil health principle, again, I mentioned already how important it is for the living roots, root exudates through that microbial necromass pathway, but it's also really important just to recapture the CO2 that's coming off from microbial activity as part of that carbon cycle. So I think at a real farmer level, field focused, practical level, like that principle for me holds a lot of really great value. I think farmers can intrinsically understand the practical benefit of it, keeping the soil covered, keeping the soil green, etc. But actually a lot of the science that we are having now is really, really backing up that kind of that kind of field level farmer focused principle. So I think that one's really valuable. But yeah, I agree. I think we need carbon cycling first. And then we can have that discussion about, okay, how do we keep some of that for the soil? But we have to be acknowledged that it's all part of that cycle. And key to that then is that soil carbon sequestration is really also dependent on stabilization. There is no sequestration without stabilization. And that's that really important part too of when we talk about the carbon cycle. Yeah, we want to bring it all in and some's going to come back out. That's fine. But then we want to stabilize. And the key to that stabilization process is, as I mentioned there earlier, the mineral associations, the chemical stabilization, or the physical stabilization, which is stabilized within aggregates. And so those two key stabilization processes are really, really fundamentally important to then that's how we capture some of that cycling carbon and sequester it. And so that's where, yes, clay soils have greater potential, as we talked about, but this is also then the other physical entrapment of carbon through aggregation, stabilized carbon. In order to optimize that process of stabilization, that's where then minimizing soil disturbance becomes really important, because when we cultivate the soil, when we plow the soil, we break apart those aggregates. And when we break apart those aggregates, we are then opening those to carbon losses. So we are undermining the physical entrapment or the physical stabilization processes within those aggregates. So that's where, again, some of that soil health principle kind of really, at a practical level, really embraces some of the latest of the scientific thinking around carbon sequestration.
Great, thanks very much.
In terms of measuring the carbon cycling, what's the best way to do that?
Yeah, so that's a big discussion too, isn't it? And I think that broadly, I would say that we have the traditional kind of more direct methods and some of the emerging more indirect methods, using satellites and imagery and much higher tech gear to try and make assessments at scale, because then, measuring carbon cycling at a field level is easy, but how do we do it across landscapes? It becomes a really much bigger question, a big problem. So we need a kind of combination of these two, and that's what generally soil scientists are trying to work on, is calibrating these and getting them kind of squared off. But the more kind of direct answer to your question is, look, at one point we have to do some soil carbon sampling. So let's just measure the carbon stocks in the soil. And again, traditionally we've done a lot of kind of just to 30 odd centimeters. A lot of the early soil carbon work was very focused on the top 30 odd centimeters. And thankfully now we're going much deeper, generally down to a meter or so, to try and assess that soil carbon stocks fully at depth. So we do have to do soil-based sampling to assess what's there in the soil. And then it's also other assessments around the biomass or the vegetation carbon. How much is actually in the plant material or in the native vegetation, for example. So doing some kind of a plant carbon assessments based on what's being stored there. And then it's really that third piece would be measuring that microbial soil respiration, the microbial activity and that soil respiration, how much of that carbon is coming off. So that kind of ultimately gives us a bit of a snapshot of what's in the plants, how much carbon is in the plants, what's carbon in the soil, and how much is kind of respiring off. And that gives us a bit of a picture to try and kind of measure some of that carbon cycling. But as I say, doing that at different scales can then become kind of quite tricky, but that's kind of what a lot of people are working on these days.
Thanks.
That's great. Nerdy scientists love to measure soil carbon and remote sensing and all that stuff, but that's not very helpful if you're a farmer. You talk to farmers all over the world, Joel. So are there any sort of simple tests that farmers can do to assess their carbon cycling or the state of the health of their soil? Is there anything they can look, feel, taste? Is there anything that correlates really well, an indicator of a healthy soil or a high organic carbon soil?
Sure. I think there's a couple here that have become quite common and maybe in recent years that I think rightly so. One of those is the infiltration test, and I think I have to agree that it is a hugely useful and beneficial indicator. And of course, very easy. Anyone can do this in the farm. Just get a ring, pour some water into it, and time how long it takes for that water to soak into the soil. So we're measuring that infiltration at the surface. And that is a really good, although it's just measuring one particular thing, it's a really good indicator, because if for that water to be able to infiltrate into the soil, that tells us that the soil has to have good physical condition. It has to have good aggregation and good porosity in order for that water to infiltrate. So if we have a well-structured soil, that's telling us that the soil is open and porous, therefore the soil can breathe. And that means that oxygen can get down into the soil and some of that CO2 can come back out, which is again what we want as part of that cycle. But when we get that oxygen into that well-structured soil, that oxygen is needed by the soil biology. The biology needs to breathe as well, just like we do. So if the infiltration is good, that tells us that the physical condition of the soil is good. Therefore, I could assume, well, at least I'm getting oxygen into the soil, then therefore my biology should be functioning quite well. And secondly, thirdly, if the biology is functioning quite well, well, then they are going to be providing that service of nutrient cycling, and therefore the soil's chemical and chemistry properties will also be more favorable. So I think that I do think that that infiltration test is a quick and easy indicator that actually gives you a bit of a snapshot into all of the soil's chemical, biological, and chemical properties. So I am a big fan of that. And you know, linking into that one is that slake test, or the aggregate stability test, just taking a clod of soil and popping it in some water and looking at how well it just holds its form, sticks together, or does it start to kind of crumble apart? And that tells us that the soil does not have very good resilience against you know, rainfall impacts, and it's not as well structured. But the point about aggregation, as I alluded to just in that last question, the last point too, is that when we aggregate soil, we pull soil particles together and aggregate them, by default we create that pore space in between. And it's actually really the pore space that's a much more important factor of soil, but it's much easier for us to measure the aggregates, the quantity and stability. But it's kind of a yin and yang thing. We can't have porosity without aggregates, but it's the porosity that really and particularly how connected those pores are, the pore space connectivity. It's the connectivity of the soil pores that is actually a really important driver of all of these kind of soil functions and soil quality type discussion. That's really what drives the infiltration. And that's also what's going to help things move around in the soil, that soil water, the gases and things move around, etc. as well, is a more porous connected soil. So I think those two are like two big favorites of mine. And then, you know, the classical, a bit of a spade test, I think is also very valuable. And with a spade test, I mean, we could be doing earthworm counts. That's going to give us a bit of a snapshot into some soil biological functioning, whether we have, you know, how many earthworms we have in a spadeful type thing. And I think linking to that is the smell. You mentioned that one. I'm a big fan of soil sniffing, I'll be honest. I think that soils that have that organic-y, forest floor, mushroomy, earthy type smell, that is a bit of a crude indicator of soil biological activity as well, because what you're smelling there is some of these organic compounds, particularly some of the volatile organic compounds that are wafting off. That's why we can smell them. And those are indicators of soil biological function. Because if that soil smells sour, for example, or a bit putrid or ammonia, anaerobic-y, well, those are the dominant smells. You're not smelling that earthy, organic kind of forest floor smell. So it is a bit of a crude indicator of soil biological function. So I'm a big fan of smelling the soil as well. And yeah, just a spade test, I think, goes a long way. You know, having a bit of a look at the soil structure, looking at those aggregates, looking at how tight that soil is or how open and porous it is, looking at the color, looking at the smell. I think these couple of tests there are very, very useful. Yeah.
Great. Good to know you don't have to have access to a mass spectrometer to learn something about the soil. Yeah.
Exactly right. Yeah.
Yeah.
Yeah, just building on that. So for farming business, for example, how do you think they can best objectively record progress soil carbon? You know, if they're thinking, for example, about future audit schemes, they might be tied into various different, you know, things around soil carbon for their customers or for the government, or just for what they want to track, what's going on with their own business, their own farm.
Yeah, you know, there's all sorts of, as you'll both be well aware, there's all sorts of ag tech out there these days. There's so many apps and gizmos and gadgets and things. It's quite a minefield. There's so many out there. But, you know, I do have to say there's a really good one in the UK, Soil Mentor, for farmers, just at a more field level and practical level. It's a really useful app in which farmers can go and do these types of soil health assessments and measure all sorts of various things. And it's just an easy platform that they can punch that information in, GPS that, and kind of track that then over time, measuring things like earthworm counts or some of the infiltration, these kind of tests that we kind of mentioned. So I think some of those kind of really farmer-friendly, user-friendly tools are very useful, just to be able to kind of put that in somewhere and then track that over time. So I think I'm kind of encouraged to see apps and useful products like that being developed to kind of help farmers keep better data records and track these things over time. So I think there are things like that are really handy. But I think more than into the discussion around some of your carbon projects and some of those kind of specific auditing processes that for carbon markets or biodiversity markets, I think the key here is that baselining is absolutely key. You have to, before you kind of go on this transition of practice change, you do need to do a level of baselining and check where your soil carbon levels are or what your biodiversity is, all these types of things. And so that does become really important. And I think that I would a little bit defer here to, any particular project that a farmer is thinking of signing up with, that they would really importantly need to read the fine print on what is the rules of that particular project and that particular opportunity, and make sure that they're following those guidelines, recording the right information accordingly for that particular project. Because there's a lot of different things out there now, as I'm sure you're aware, and so it's just everyone does things a little differently. So just making sure that we kind of collect the right information for that particular project. But I just think I would emphasize the importance of that baselining. You've got to start somewhere first, and then we can kind of that way track the changes over time.
Great.
Thanks.
Thanks very much for talking to us, Joel. That's been fantastic. We've had a very wide-ranging discussion. And don't forget, you heard it first that Joel is a soil sniffer. You heard it here first. Yeah. Thanks very much.